Criteria for selecting the calculation method. Welcome, everyone. In our previous lessons, we explored 3 distinct mathematical approaches to calculate the arithmetic mean of grouped data. Specifically, we looked at the direct method, the assumed mean method, and the step-deviation method. Now, it is important to remember that even though these techniques look different, they are all mathematically equivalent. This means that all 3 methods will yield the exact same result for the mean, which we denote as x bar. However, the real challenge isn't just finding the answer, but finding it efficiently. Depending on the nature of your dataset, the amount of effort and time required for your calculations can vary significantly. In the following slides, we are going to learn how to strategically choose the most efficient method. By doing this, you can avoid tedious, heavy calculations, and most importantly, reduce the likelihood of making simple arithmetic errors. Let's dive into how you can decide which method to use. 1. The direct method. Now that we have established that all 3 methods will lead us to the same final answer, let's dive into the first one, the direct method. As you might have guessed from the name, this is the most straightforward approach we have. The process is quite simple. You take each class mark, which we call x sub I, and multiply it by its corresponding frequency, which we call f sub I. But as a mathematician, I want you to think about efficiency. You shouldn't use this method for every problem. You should specifically choose the direct method when the values of your class marks, x sub I, and your frequencies, f sub I, are small and manageable. A great rule of thumb is to use this method whenever the sum of f sub I times x sub I is easy enough to calculate in your head or with quick scratch work without needing a calculator. The reasoning behind this is quite logical. Because this method doesn't require any intermediate subtractions or divisions, unlike the more complex methods we are about to discuss, it is actually the fastest and most direct way to handle simple datasets. It keeps your workflow clean and minimizes the steps where you might make a mistake. 2. The assumed mean method. As you might have noticed in your practice problems, as the values of our class marks, x sub I, start to increase, the products of frequency times class mark, f sub I times x sub I, can become very large. This makes the summation process quite cumbersome and increases the risk of making a calculation error. The assumed mean method is designed to simplify this by essentially shifting the data to a more manageable range. So, when should you choose this method? You should use it when the class marks, x sub I, are large numbers, or when the frequencies, f sub I, are also large, making that direct multiplication we just discussed very tedious. The reasoning behind this is quite clever. Instead of working with the original large numbers, we pick a value to act as our assumed mean, which we call a by subtracting this assumed mean from each class mark x sub I. We create what we call smaller deviations, denoted as d sub I, which equals x sub I minus a. By doing this, we are multiplying our frequencies by these much smaller deviations instead of the original large class marks. This significantly reduces the size of the numbers we are working with, making the arithmetic much smoother. We will see a perfect example of this in the next few slides when we look at some real-world scenarios. Now that we've seen how the direct method works for simple datasets, let's move on to our second option, the assumed mean method. 3. The step-deviation method. Now, let's move on to our third and most advanced option, the step-deviation method. You can think of this method as a natural extension of the assumed mean method we just discussed. While the assumed mean method helps us by subtracting a central value, the step-deviation method takes it one step further to reduce the size of our numbers even more. It does this by taking those deviations we calculated and dividing them by the class size, which we represent as lowercase h. So, when exactly should you reach for this method? First, just like the previous 2 methods, it is ideal when your class marks, x sub I, and your frequencies, f sub I, are quite large. However, there is a crucial condition you must check. You should use this method specifically when your class intervals are equal, meaning you have a uniform class size, h, or when all your deviations, d sub I, share a common divisor. The reasoning behind this is quite brilliant in its simplicity. By dividing the deviations by the class size, we effectively convert those large, cumbersome numbers into very small, manageable integers, such as -2, -1, 0, 1, or 2. By doing this, we minimize the multiplication effort to the greatest extent possible, making your calculations much faster and significantly reducing the chance of making a silly arithmetic error. Real-world application scenario. Now that we have understood the theory behind each method, let's move from abstract formulas to a real-world application. To help you visualize how to choose between these methods, I want you to imagine you are working as a data analyst in a large logistics warehouse, where your job is to record and analyze the weights of incoming parcels. Now that we have understood the theory behind each method, let's move from abstract formulas to a real-world application. To help you visualize how to choose between these methods, I want you to imagine you are working as a data analyst in a large logistics warehouse, where your job is to record and analyze the weights of incoming parcels. Let's look at our first scenario, which we'll call Scenario A, involving small parcels. In this case, the weights are quite light, falling into small ranges: 0 to 2 kilograms, 2 to 4 kilograms, and 4 to 6 kilograms. If we look closely at our observations, the class marks, which we denote as X sub I, are simply 1, 3, and 5. Because these values for the class marks and the frequencies are so small and easy to work with, you don't need to complicate things with deviations or class sizes. Your best decision here is to use the direct method, as the multiplication is straightforward and the risk of error is very low. This sets the stage for our next scenario, where the weights become much more significant. Real-world application scenario, continued. Now, let's move from our example of small parcels to something a bit more substantial. Scenario B, which involves heavy machinery. In this case, notice that the weights are much larger, with class intervals ranging from 500 to 550 kilograms, 550 to 600 kilograms, and 600 to 650 kilograms. If we take a look at our observations, the class marks, or X sub I, are 525, 575, and 625. If we were to use the direct method we discussed earlier, multiplying these large class marks by their frequencies would result in very large, cumbersome numbers, making the calculation quite tedious. Therefore, our best decision here is to use the assumed mean method. By picking an assumed mean, let's call it A of 575, we simplify our work significantly. Instead of multiplying by large values, we only have to multiply the frequencies by the deviations, which are simply -50, 0, and 50. This brings us much closer to the efficiency we'll see in the next scenario involving even larger industrial shipments. Real-world application scenario, continued. Now, let's look at our final scenario, which brings everything we've discussed together. Imagine we are dealing with Scenario C, industrial shipments. In this case, the weights are not just large, but they are also perfectly consistent, meaning we have uniform intervals. Specifically, we are looking at weight ranges from 1,000 to 1,100 kilograms, 1,100 to 1,200 kilograms, and 1,200 to 1,300 kilograms. If we observe the data, we can see that the class marks, or the midpoints, are 1,050, 1,150, and 1,250. Additionally, our class size, which we call H, is 100. Now, following the logic from our previous examples, you might ask, which method should we choose? Because the numbers are very large, the direct method would be exhausting, and while the assumed mean method would help, we can actually do even better. My decision here is to use the step-deviation method. Here is why. By picking an assumed mean, of 1,150, and then dividing our deviations by our class size, H, of 100, our multipliers simplify beautifully to just -1, 0, and 1. As we will see in our summary table in the next slide, this is the most efficient way to handle large, uniform data because it reduces the complexity of our calculation to the absolute minimum. Summary table for quick selection. Now that we have looked at each method individually and seen how they apply to different real-world scenarios, let's bring everything together with this summary table. This will serve as your quick reference guide for exams. First, let's look at the direct method. As we discussed earlier, this is your go-to approach when you are dealing with small values for both the class marks, x sub I, and the frequencies, f sub I, because the numbers are small. The complexity of the calculation is low, making it highly efficient for simple datasets. Next, we have the assumed mean method. You should switch to this method when you notice the class marks or the frequencies are becoming large, which we saw in our heavy machinery example. The complexity here is medium because you have an extra step of finding the deviation, but it remains highly efficient for large data because it keeps your multiplication manageable. Finally, there is the step-deviation method. This is the most advanced option, used when both the class marks and frequencies are large, provided that you have a uniform class size, which we call H. While there is a bit more setup involved initially, the complexity of the actual calculation is actually very low because you are working with tiny integers. This makes it the most efficient method of all when dealing with large, uniform datasets. Keep this table in mind as you practice. It will help you decide instantly which path to take to save both time and effort. Now, before we wrap up, I want to highlight a few common pitfalls that students often encounter when applying these methods. Common mistakes to avoid. First, try not to overcomplexify simple data. I often see students using the step-deviation method even when the numbers are very small, like in our first scenario with the small parcels. While it technically works, you are adding unnecessary extra steps, such as calculating the assumed mean and the class size. This extra work actually increases your risk of making a sign error. Remember, if the class marks and frequencies are small, stick to the direct method to keep things simple and fast. Second, be very careful not to ignore the class size. As we discussed in the step deviation section, that specific method relies entirely on having a constant class interval, which we call H if your class intervals are not equal, meaning the width of your groups varies. You simply cannot use the step deviation method. Always check your data intervals before deciding on your approach. Finally, and perhaps most importantly, do not forget the final adjustment. This is where most marks are lost in exams. When you use the assumed mean or step deviation methods, you aren't just calculating a simple sum, you are calculating a deviation from a starting point. Many students successfully calculate the sum of frequency times deviation, but then they forget to bring the value back to the original scale. Always remember to complete the formula. For the assumed mean method, your final answer must be the assumed mean, A plus the sum of frequency times deviation, divided by the sum of the frequencies. And for the step deviation method, you must add the assumed mean, A, to the product of the class size, H, and the sum of frequency times U, divided by the sum of the frequencies. Now that we have seen how to choose the most efficient method using our real-world scenarios, I want to pause and discuss some common pitfalls. Even when you know which method to use, it is very easy to make mistakes during the calculation process. Let's look at 3 specific errors you should avoid. If you keep these 3 points in mind, you will not only find the correct answer, but you will also find the calculation much more manageable. Now, let's wrap up with our key takeaways. Key takeaways. First and foremost, I want you to remember that the choice of method is based entirely on computational convenience, not on the final answer. You aren't choosing a different method to get a different result. You are simply choosing the path of least resistance to make your life easier. To keep it simple, just remember these 3 rules of thumb. Use the direct method when you are dealing with small numbers. Use the assumed mean method when you encounter large numbers. And finally, use the step deviation method when you have large numbers combined with equal class intervals. As we have seen through our various examples and the summary table, regardless of the method you choose, the value of the mean, x bar, will always remain exactly the same. Whether you take the long way or the short way, you will always arrive at the same destination. All right, we have reached the end of our lesson, So let's wrap everything up with these key takeaways to ensure you have a clear roadmap for your future calculations. Great job today! Make sure to review the common mistakes we discussed earlier to ensure your calculations remain accurate.